Okay, so before we get started, I have a small survey to do. So we're going to talk some about Python Wednesday and into Friday. And so I'm just curious, how many of you have some familiarity and some have used Python some in the past? Okay, so sort of a smattering of you, maybe a quarter of you. Okay, so that's helpful. And how many of those of you who have used Python, how many of you are reasonably familiar with NumPy? Okay, so some of those. Subset of people. Okay. Okay, so we had finished off talking about S3 classes, and we had launched a little ways into talking about S4 classes, and I left you with the little problem of if I just type Q here at the prompt, I want the behavior to be that it will just quit out of R and quit in a clean sort of way. So the idea of this little problem is just that it's a good little check of our understanding of how S3 classes and methods work. That's interesting. Oh, I see. Okay. Okay, so I asked you guys to think about that. So if I just type Q at the command line in R, what is R behind the scenes going to go and try and do? Okay, so either it's going to know there's a Q function, so either it's going to try and call that function. But if I just type Q, it's not actually trying to evaluate the function. It's just trying to look for an object, right? So it doesn't actually go and then try and call this function because I haven't put the parentheses there to tell R such that R does not recognize that what I'm trying to do is make a function call. So if I were instead to just type if I were to type something else, all right, that's a bad example because that exists. So all right, all of these things exist. If I just type A, right, it says A is not found. But if A is found, what is it actually going and doing when I type A? Okay, so it's calling print. So what it's actually doing is let's create A again. So A equals 3. And now if I just type A, what it's really doing is it's calling print of A, right? And we've already seen this idea of generic and class-specific methods. So by default, it's just going to call some print.default. But suppose that we want there to be some other behavior when it tries to do this printing. What can we then do to try and to solve this problem of being able to quit by just typing Q?
Assign something.
Say it again.
You assign something.
Well, what do you mean by assign to print?
Like if you use a function and you see print.function and you assign it quit.
Okay, so I do want to have some function that will do the quitting. But Q, well, I mean, I guess Q could be a function, but we could think of making another Q. Right? We don't have to use the Q that is in the whatever base package or wherever it does quitting. Sorry, I lost my train of thought. So what mechanistically would I need to do to get this set up? Hello? Okay, so I need to make an object Q, and then I need to make sure that that object is in some class, and then I need the print method for that class to basically go and do this quitting. So I would need to do something like Q is a list, say, and then I need to assign it some class. So I could say this is the close R class, for example. Okay, and then I need to say print.closeR is some function, and oops, that's not what I meant to do. And then I would need to say that what it's going to do is just quit and in this case, if I wanted to close cleanly without doing anything, I think I would need to say save equals no. Or I guess I'd have to go back and look and see what. Oh, save equals default. So presumably, if I say save equals no, that may work. Okay. So any questions about the structures the mechanisms I've set up here? So hopefully this will now work if I just go ahead and do it.
Yes.
Oh, right. It has to take the actual object, right? Because this is a method, and so if we go back to our S3 methods, when we were talking about setting up those, where's a good example in here? All right, so we made an S3 method here that was a class-specific summarize method, and so it needed to take object as its argument. So let's go ahead and go back and redo this, and then. Oh, that's interesting. So I wonder if this would work. I think I have exactly this in my own R profile file, and it works if I'm just using the command line version of R. So I think what might be going on here is some interaction with using RStudio where it didn't like that. But I don't think there was anything wrong with what we just did. So I think I might leave it at that and chalk that up to the vagaries of RStudio. All right, so where was I? Okay, so any questions about that? Yeah, Dustin.
Is there a reason you have to assign Q an object? Couldn't you just define the function, then add a class, and then just the Q?
So you want me to make a new Q function? Sorry, so say your question again?
Couldn't you just define Q as, you just define like print dot whatever as your function Q, and then you just class Q of that thing, and then you use Q. Like you don't have to define the list.
I don't have to define the list. Well, I need the object then. What I was doing was when I was typing Q, it was then going to look for the print method for an object in that class. So what you were saying, just do what? Print.
You just omit the first line of the thing you define. Like instead of doing those 3 lines you did, you just do the last 2.
But so omit the Q equals list?
Yeah.
Okay, but if Q doesn't exist, well, right, because Q exists as a. Okay, so I don't think that will work because if we just type Q and we hadn't defined it to be a list, so then we don't have an object called Q in our global workspace. The object Q that exists, there does exist a Q, the quit function, that exists, I think, in the base package. So if I do all of the rest of that with the print.q, so I said, so let's see, so what did I did this. And is that what you want me to do?
Yeah.
Okay, so now.
Then you assign class Q close R.
Okay. Okay, so I guess that worked in the sense that it got us to the same place as this before. I think maybe the problem is that let's do help on Q. Maybe no is not the right not one of the options. Oh no, it is. Okay, so I'm still not sure what's going on with that. I think the reason I probably would not want to do that is because it's a little bit weird in that when we did class of Q gets close R, we're basically saying now if the class of Q is that function that does the quitting. So we're sort of basically taking this object that is in the default, in the base package, and assigning it some new class, even though it is a function. So I think it seemed like it worked, but it seems like a bit of a hack in that I think it's cleaner to make our own queue object and then have that queue have its own class. Because that way we have our queue object and we have the queue function, and they're distinct, and we're not sort of messing with the queue function. I'm actually sort of surprised this worked, because the queue, I mean, if we do that and then we do this, yeah, so basically what seems to have happened is I've basically sort of tacked this on to the original function, which is sort of, I'm glad you pointed this out, because I guess it does point out that this sort of works, but it does seem like it's a bit messy. Other questions or comments? Okay, so let's go back and say a little bit about S4 classes and about reference classes. So, where was I here? Okay, so I said, okay, we can set these S4 classes. We have to formally define what the slots or the components of the class are, and then we can make a new instantiation of an object in that class. Another thing that we can do is actually use a function called setValidity that will basically allow us to do some checking of the elements of the components or slots in the class. So this would be an example. Again, this is a little bit silly, but this is checking the validity for this indiv class that I created. And all it is some code that I write that basically checks to see if I have valid ages and a valid age and a valid name in the class. And so then when I call new, it will behind the scenes also run the setValidity function and basically do these checks to make sure that things that are coming in are reasonable. So if I do this, looks like it prints back a little bit of stuff about the class. And now if I try and give a name that's some crazy string that has a digit in it, you'll notice my checking does a grep for numbers in the name, and will reject the validity if that's the case. And so you can see this then it is good behind the scenes using that function, and it doesn't like that. So we could be more or less sophisticated about our checking. Here I'm going to do something where it doesn't complain about this because I wasn't all that careful about making sure to check for other kinds of weird, crazy names. But the idea, sort of the main point, the main reason I mentioned this was just to reinforce this idea that the notion of S4 is that it's more formal than these S3 classes. Another thing that I'll mention is we can just assign into the slot of the object, and that will change the slot directly. For those of you who are used to object-oriented programming, I don't believe that S4 classes have the notion of a private slot or a private member object. So you can just sort of manually go in and change the inner components of an object in a class. This is if you're sort of programming more formally, you might complain about this, because part of the idea of doing object-oriented programming is basically to hide the guts of what's going on inside the class away from the user on the outside. So the general way that you would want to do this in a more general sense, sort of in any language, would be to have functions that go in and set particular attributes or values in the class, and get functions that go in and retrieve them, so that you're not actually explicitly using the @ symbol. And the reason being behind that way of thinking about things is that if you provide an interface to the user where they don't have to know what the names of the components are inside, then you can monkey around with the insides of the class. And as long as you keep an interface that the user is used to, that knows how to use, then you could have an age slot in the class, but maybe later down the road you modify your code and all of a sudden for some reason you don't want to have an age class, but you want to represent the age in some other way. Well, if your user is always changing ages by doing this, then as soon as you change the innards of the object, you're going to break their code that tries to just use the slot directly. Whereas if you have functions that do the setting and the getting, then you can monkey around with the code in the inside all you want, as long as you continue to provide those functions that do the getting and setting. So that's sort of one principle behind object-oriented programming that R doesn't really fully allow you to do here. Okay, so then just a little bit about S4 classes in terms of setting generic and class-specific methods. The syntax is different, but the concepts, are the same as we've already seen. That we need to, if I want to make an isVoter method for this class that would check whether a given person is of voting age, I need to have a generic function. If that generic is not already defined, then I need to write the generic myself, but that's pretty easy. All I need to do is just call this function setGeneric, and then it's going to make use of this standard generic function. This is basically, again, setting up the dispatching so that when I call the generic method, the generic function, it then knows to go look for a class-specific method relevant for whatever object was passed into it. And then I can create a class-specific method function, and then I need to formally assign, in S3 I didn't need to do this formal assignment, but in S4 I need to formally assign this function as the isVoter method of the indiv class. And then once I do that, then I can go ahead and call isVoter, and it should work with an object of this kind, of this class. So then I guess I still have the crazy name in there, but it returns back this information where I checked on the voting age. Okay, questions or comments? And then I think the last main thing I'll mention here is just that we can have inheritance, as we did for S3 classes, this idea that we might have a new class that is built on on another class and has some additional features or characteristics. So for example, I have my class indiv, but maybe I want to make a class called the Berkeley individual that has some additional information, like it might have the person's Cal ID in it. So then you do this thing where you set the representation, so you set what the slots are, but then you also say contains, and this gives the class that this new class is going to inherit from. And it's going to inherit all of the original components and methods that the indiv class had. So I can still call isVoter, even though I haven't defined an isVoter method for the Berkeley indiv. I have defined an isVoter method for the indiv class, so I can therefore use it here as well. And just like with LM and GLM in the S3 context that we've already seen, this new object is not only going to be a Berkeley indiv, but also going to be a member of the indiv class. So I think that's more or less all I want to say about S4, about the S4 stuff in R. There's a little bit more detail in the notes that you can go ahead and take a look at that has to do with inheritance and using S3 classes within an S4 class, but I don't think I want to go into that here. So then the last thing I want to say about object-oriented programming is this new thing called reference classes. So the idea of reference classes is to allow you to have a class where you can basically do different, where you can call a method on the class and modify the elements of that class in place without having to return the whole object back and reassign it. So basically, it's a way of getting around the pass by value semantics that R has. So this is just a few years old. If those of you who are familiar with Python, some of the things in this will look reasonably similar to you as to what you're familiar with in Python. So what I'm going to, in terms of object-oriented programming in Python, so this is an example, and what I'm going to do is just do an example where we have, where we create a class called this tssim class, and this is basically the same functionality as I showed you for another example earlier in this unit, although I'm forgetting exactly the context of this example. But the basic idea was I have a set of time points on a grid in this particular case, and I define a correlation function, and I use that correlation function to compute a two-dimensional matrix that's all the pairwise distances between those time points. And then I generate a Gaussian process with the correlation function such that I'm basically I'm generating a stochastic process that varies over time in some smooth way. So in order to do that, if you recall the other example, I need to compute this distance matrix with all pairs of distances. I then need to compute a correlation function, a correlation matrix from that distance matrix. I then need to compute a matrix decomposition, in particular Cholesky decomposition, and I need to multiply the resulting matrix by a vector of standard normals, and that will then generate my discretized version of my stochastic process. So in order to do all that, the idea is I might set up a class that will hold the components that I need, and then some methods that will do these various operations to generate these kinds of stochastic processes. So I'm gonna set up my class with a call to the setRef class function, and I'm gonna give my class a name. So I'm just gonna give it in quotes the same name as what I'm calling the resulting class as an object. And then I'm gonna define what the different member object components are in this class, and they're the sort of things you might expect you would need, like the grid of times, the correlation matrix, the lag matrix, and the distance matrix, a parameter that is in part determines what the correlation is. This is the Gillespie factor, the matrix decomposition, and I need to say what kinds of objects these are. So again, this is somewhat more formal than we're used to in R, because we're having to say in advance, define the types of the classes of our objects. Okay, so you give it a list which contains the fields or the slots or the components, however you want to call these things. And then you give it another list that contains the different methods that I want to be able to use with my class. So this is just a list of functions. And initialize is what's going to be called when I try and create a new one of these things using new, as we'll see in a minute. So here's my initialize method, and it in this case just loads a package that I'm going to need, the fields package, and it then just assigns to some of the fields or slots of my that we just saw when I was defining what the slots were. And you'll notice the use of the assignment operator that we've seen within the last week or two, that what this means in this context is this is basically saying, this is taking some inputs. You'll notice the names of the inputs of the input arguments are the same as the names of the fields of the function. And so when I do something like this looks a little weird because I'm using the same thing on the left-hand side and the right-hand side, but this is being taken to be the input argument, and then this double left arrow assignment operator is assigning into the field within the object. So it's assigning into the core param that was defined here as one of the fields of the object defined here. So with this, if you recall back to this idea of using closures and setting up and using that assignment operator in the context of a closure, where within a function we assign into the enclosing environment, this is really that same functionality. And I believe the person who developed these reference classes, who's John Chambers, who's very well known for basically developing S, which is the precursor to R, he was basically, when he set this up, he was basically working off this idea of a closure, so sort of extending that idea. Okay, and you need to do this thing called call super, which is basically calling a sort of default method for initialization that sets some other stuff up behind the scenes. And you'll notice in my initialization, I also call another method that calculates some of the matrices that are involved. So here's that calcmats function. This is the second. The first method that I have in my list was this initialize. Then I have this calcmats that calculates the lag matrix or the distance matrix, and then from that calculates my correlation matrix, in this case just as an exponentially decaying function of the distance, the lag between any two times. And then I do my Cholesky decomposition here. So this does all the matrix calculations that I need. I have another sort of helper function that allows me to change the grid points that I'm using to make my discretized stochastic process. I guess maybe I should have made a picture before. So the idea is I have a grid of points, and I'm going to generate a stochastic process as just a set of points from that, a set of values from that process that if I have a fine enough grid, will basically trace out what this process looks like. And then I have a print method, but for reference classes, you have to call it show, and this just in this case prints out some information about the object. So in this case, it looks like one of the things that it nicely does. I made this syntax error and then I left it in just for illustration, which is if you would try and assign locally without using the global assignment operator, then it will give you a warning and say, did you really mean to assign to lagmat? Because this is just assigning locally to lagmat within the frame of this calcmats method. It's not assigning into the lagmat field that's the field within the overall object. So it gives a little warning. And then if you want to, you can add additional methods after having defined the class. So this here is the end of defining the fields and the methods for the class, and then I decided after the fact I was going to add an additional method in. So I said, oh, I forgot to actually add the simulate method that will actually generate this stochastic process. So that method I added on here. So let's actually go through and just run this quickly and see what things look like. So I'm going to create the class. You can see it gives me a little bit of information about what's in the class, what are the fields, something about what the methods are. I'm going to add on this additional simulate method. And then if I want to do the construction or the initialization, then I call this function new. So what I do is I take the name of the class, I do $signs, this sort of looks like an S3 sort of thing. I do new, and then I pass in whatever the input arguments are. And this then goes behind the scenes and calls that initialize method. So that should set up that. You notice I had injected a little print statement that just gave the user an indication of what was going on. And now if I type master, then this is calling the print or the show method behind the scenes that I had set up. So it prints it out in this nice format instead of sort of just like regurgitating a whole bunch of unformatted stuff. And one thing I think I forgot to mention is you basically put the help information directly into the methods, and you do it in a form that sort of looks like, those of you who know Python, is called a doc string. So you basically put the string, you basically put a character string here below, just below the definition of the function of the method, and that is what gets printed out when you call help. So I can call help on the calcmats method, and it will print out that information that I had put in the code about what this particular method does. So then I can call my simulate method for my particular instantiation master by just with some syntax like that. And in this case, it's going to return the devs, which are just I'm going to call the resulting output devs, which is because they're the simulated values. And I can go ahead and plot what they look like. And here I've generated a stochastic process. This has an exponentially decaying correlation function, so it's fairly jagged in terms of its. It's not all that smooth in terms of its behavior. Okay, questions so far? So when I was doing all this, you'll notice I didn't, for example, I guess I haven't done all that much here, but I didn't have to pass back and reassign the output of doing these different things. All the stuff was changed in place in the object and in the fields of the object. So if I want to make, it's interesting, if I want to make a copy here, if I can say my copy just gets assigned to be master. But it turns out that's not actually going to make a completely new copy. It's basically just going to make a pointer to the same object. So if I really want to make a copy, then I have to call the copy method, which is a general method that we can use with these reference classes. So I have to say master $copy to call the copy method on my master object. And then that's going to make what, in some cases, people will call a deep copy, which is actually a true, separate, explicit copy of the object. So this change times changes the grid field within the time. I think I called it times. The times field within the object. So I'm going to change it within the master object by doing that. And now I'm going to look at my copy and my deep copy at the value of times. So my copy of times should look like the same as master times, the original one, because my copy is just a pointer to it. But my deep copy retains the original values that I originally had in the master object because it is an explicit new copy. It is an explicit new piece of memory where the object is living. Okay, so I think that's basically all I wanted to say about these reference classes. Any comments before I move on from object-oriented programming in R? Okay, so the last thing I wanted to say in this unit was to talk some about what's called computing on the language. So there is a little short section on working with environments that I'm going to skip over, in part because what I show you there is basically somewhat redundant now that these reference classes exist. But do take a look at that on your own just to get a better sense of working with environments, which we've already done to some degree. Okay, so I want to skip over and talk a bit about how R basically takes code and processes it and prepares it such that it can then evaluate that code and create output. And I think it's helpful just to have a basic understanding of how this goes on behind the scenes. And sometimes this turns out sometimes you might end up needing to actually exploit this at some point. So basically, what R is doing is that you're giving it either one line of text or some multiple lines of text that it then needs to process and go through and interpret and figure out how to work with. And you may have many nested statements, and it needs to go through and figure out how to work through all that nesting to then evaluate the code in the correct manner. So basically, what's going on is R is basically ingesting that code, and it's basically translating that code into functional form such that it can then evaluate the functions. So what it's basically doing is setting up what's called a parse tree that basically allows it to then work its way through the nested function calls and figure out what all the necessary arguments are for evaluating the code. So for example, if I suppose I had a somewhat complicated expression like this. So there are now multiple R functions that need to be evaluated to run this code. So basically what R does is it goes in, and there's a parser that goes in and works its way through this code in a recursive kind of manner. And it basically sets up a tree where it's doing something like this. So the mean function has to get called with an argument, but that argument itself is the result of running some functions. So this basically then gets, the next thing that it sees is, you know what, this is basically the plus function with 2 arguments, and the result of that is what gets fed into mean. So you can think about what it does is it actually says, oh, I need to actually evaluate the plus function, and that has 2 arguments. In this case, this concatenate call and this rnorm call. So it's then, on this side, the first argument is going to be a result of calling the concatenate function, and on this side, the result of calling the rnorm function. Well, the rnorm function in this case only takes 1 argument, although by default there are another 2, the mean and the standard deviation arguments. So depending on how we want to represent this, we could, I guess, represent this either as just 3 or as the default mean, the mean is 0 and the standard deviation is 1. And then this is taking, in this case, 3 arguments as well. So this is basically how R is representing this code. And then once it then has it in this representation, it can then sort of basically work its way up from the bottom, evaluating the pieces, filling them in as it does the evaluations, and then it's able to then evaluate the plus once it's done this, and then once it's evaluated the plus, it's then able to evaluate mean. So it's working its way through things in a very structured sort of way. So we'll see a little bit more about that in a second. The other thing I want to mention here is, we've already sort of touched on this a few times during the course of the semester, which is that behind the scenes, R is basically a C program, and it's basically calling C code in the guts of it. So when you look at R code, in some cases you'll basically see native R code, and then other places as you delve deeper into the code, you're going to see calls that are basically going off directly to compiled C code. And those calls, whenever you see something like .internal or .primitive or .external, those are calls to C code. In general, though, once you get to that point, you'll know that code is going to run pretty quickly, because that's just calling compiled C code as if you had written your own C program, compiled it, and then gone ahead and run it. So if, for example, we think about how does, say, the plot function, what happens when we actually call the plot function on some vectors? Well, if we call plot and we give it 2 vectors as arguments just to make a scatter plot, unless there's something fancier going on in terms of the objects that get passed in, that
plot is just an S3 method. It's a generic method. It's going to see that, oh, you're just passing me 2 standard vectors, so I'm just going to go ahead and call plot.default, which is the default method. It turns out if we look in the guts of the code of plot.default, we'll see that most of the actual plotting is being done by a function called plot.xy. So we're now like 4 levels deep in terms of the processing of what's happened when we call plot. And if we go in and look at what plot.xy does, well, presumably plot.default has done some machinations to set things up, and it looks like maybe it's just passing in a single object that has both the x and the y information. So I don't know exactly what the form of that is. I don't know whether it's a list or a 2-column matrix or what it is, but if we wanted to, we could look in more detail. But then you'll notice that all plot.xy does is it just returns using invisible the result of calling .external.graphics and then the name of some presumably C function that gets called, and these arguments that are going to get passed along to C. So deep down within, these multiple layers of having worked our way through what happens when you call plot, we see that, oh, it's actually, I don't know exactly what the difference, what it means by when it has .graphics here, but it's calling .external in some somewhat modified form. So it's calling some C code that has this name, the actual C function has this name, and then these are the arguments that get passed along. So this is sort of a common thing if you're sort of working your way through and trying to figure out what's going on, is you'll often work your way through, you'll see that there are 3 different R functions that are called, and then eventually you'll see there's some C code that gets called. If you were just, for example, looking at the matrix multiplication operator, you'll see it's much more simple. It's just a function call where it directly calls .primitive, so that's calling some C code, and it's calling some C code where the C function or C operator has this particular name. And if you want to, it is possible to actually download the source code for R and actually go and look and see what is the actual C code that gets called here and what's the actual C code that gets called here. And occasionally that can be handy for just understanding actually what is R doing really behind the scenes. Okay, so any questions or comments about that? Okay, so the next thing I want to talk about is basically just how you would go about manipulating R code as code instead of actually evaluating the code. So in general, if we just type in some R code and hit return, what R does behind the scenes is it goes through this process of setting up this tree, and then it actually evaluates the code. So the idea is that we need a way to intervene. If we want to manipulate the code without actually evaluating it, we need a way to intervene in that process of creating this tree and parsing the text and parsing the code and creating this tree and actually evaluating it. So the way we do that is either using the quote function or the expr function, and both of which work in pretty similar ways. So the idea is that if you call quote with some R code, it will do this parsing, but it won't actually do the final step of actually evaluating the tree or evaluating the code and getting the result. So let me switch over to R and we'll actually see this in real life. Okay, so I'm going to call this little if statement. This if statement just checks X and either returns out of the if statement either orange or apple. So of course, if let's say X gets 3, and then if I actually just run this code, it's going to presumably produce orange or apple as is appropriate, right? So if I actually want to capture the code, then I need to wrap that call within the quote function. Okay, so that's now contained in my obj object. If I just type obj, what is that going to do? That's going to call some print method on obj. Turns out that's not actually all that helpful because it just sort of prints back what we already passed into it. But it is nice to at least verify that R has sort of captured the code without actually evaluating it. So one way to look at this is to actually convert it into a list, and when we do that, R is actually going to show us the parse tree in a form that looks something like this. So I can do as.list of that object. Actually, let's just first see what the class of that object is. Oh, okay. So if I do as.list of that object, we can see that what it does is it creates a list that sort of gives us, it's sort of a representation of this, although it's sort of flattened in a certain way. So the first thing it says is that this is first thing is if, just indicating that that's the call that we're making. We're making an if statement call. And then the second thing is the condition, so that's basically the first argument of the if statement. And then the third and the fourth things are the result of if true or if false. So those are the things that are the third and the fourth items here. And when I did class of object up here, it says it's an if object. So that's basically a language object that is basically a certain type of call, in particular the call to the if functionality. So we've already talked about this idea that basically everything in R is a function call. So I could have instead of parsing the usual way of writing the if statement, I could have parsed calling the if function with 3 arguments. And if I do that, again, I'm going to wrap that in quote so that I don't actually evaluate it. And now I'm going to say, are those two things the same? And it says, indeed, obj, which was the thing created by the usual call to if, and using this if function, the result of parsing that gives us the same resulting language object. Okay, questions at this point? Okay, so I can do the same sort of thing with even simpler code. So I could say, let me create an X that has 3 in it. But if I wrap that in quote and I say, what's the type of that? It says, oh, it's actually a symbol. So it's basically just if I think about the abstraction of what X is, well, X is the value, contains the value 3. But if I think of X as one of these language objects in a more abstract sense of the code, it's a symbol that basically just points to some memory location, and in that location is the value 3. So we're sort of abstracting away from actually working with the code to thinking about the code in this more one-step bigger picture sort of way. I can also use the expression function, and basically there's not too much difference between expression and quote, except that if I wanted to pass in multiple statements separated by commas, I can do that with expression, and it will basically return to me a vector of these language items instead of just a single one, which is what quote was giving me back. So I can do things like that, and then if I look at A, it says, oh, it's an A in this case is now. Remember, I just did an example where I created an object that was of the if class. Here I've created an object that's of the assignment class, because that's the actual function that's being called here is that it's doing an assignment with the arguments x and 5. And then for B, I did 2 different assignments separated by commas. And if I look at so B is an expression object. But now if I try and burrow my way into B, the first piece of B is just the same as what A is. So A, I said, was just the statement x gets 5, but the first element of B is also x gets 5. And if I asked what's the class of that, it would say indeed that is also an assignment, and that those two things are equal. So let's step back. I'm going to switch over to the notes and just show you this table that I created to try and get a little bit of clarity on what the classes and what the underlying fundamental types of these different things are. So if I think about the code that's represented as just the value x, well, that's just the name of an object, and its underlying type, sort of in the guts of R in terms of the C, how things are stored in C, is that it's a language object, but a particular kind of language object called a symbol. So basically, just the name for an object. If I actually wrap something in expression, then it says these things are expressions. But then if I burrow down into that, I can see that this is just going to be an assignment operator with assignment call with 2 arguments. And then basically, anytime I do anything that's like a function call, the result is going to be that they're of the type language, and they're various kinds of calls if we ask what class they are. And some of these are sort of specialized types of calls, like an assignment or for statement or an if statement, and others are just if you use class on the object, it will just tell you that it's just a call without any particular specialty type or kind. So as you'll see in the code in a minute, if I do class of quote of these sorts of things, this is the result that I get back. So that's how R is sort of interpreting these things at the level of the language. And basically, anytime you run anything that's like a function and evaluate some and make any sort of call that runs some code, you're basically creating an object that's in this that's one of these call kinds of objects. So these language objects are not actually officially lists, but you can sort of think of them as being lists, as we've already seen. So this is what I did to basically create that table. Was I created these various language objects using quote, and then I said, oh, what's the class and what's the type of each of these things? And so if I do that, then what we get back is basically what I just told you based on what was in that table. It'll print back the class and the type for each of these different things. There's that if statement, et cetera, et cetera. Okay. So I can go ahead and I'm going to create a few more of these different kinds of language objects. And what I want to do here is just burrow down into them a little bit and look at the nested structure of these things. So let's see. So I can do things like I can say, okay, let's express that E1 as a list. Well, that's just a single element list that has this language object x gets 3. But then if I burrow down into it, I can say, what about as.list of the first element of that? And that now shows me the sort of parse tree or the parsed version of the code where it says, oh, this is an assignment call, and here are the arguments coming into that assignment call. And if we had a more complicated one, like we had created a language object like this, then we would see that there was this level of nestedness. So that's the sort of thing that you can play around with and actually see explicitly here. Let me see, is there anything else I want to mention here? Let's see, if we do this one, we can say as.list of E3. And we see that indeed is just a call to R norm, and then it has the argument 3. So here's sort of an interesting one that we might not have expected. So if I do, so E0 was just I wrapped the number 3 within quote to try and make it into one of these language objects. And if I then ask what are the class and the type of that, it just says this now looks like the sort of thing we expect when we look at classes and types of R objects. It says, oh, this is just a numeric, and underlying that in C, it's stored as a double precision floating point number, a decimal number. But there's sort of an interesting thing that we see if we actually look at a negative number, which is I'm going to do the same thing with a negative number. And now if I ask what's the class and type of this E4, I might expect that it's going to give me back the same thing as did when I did with E0, which was just the value 3. But if we actually do this, it says, no, wait a minute, -7 is actually a language object, and it's actually a call. So it's not actually interpreting -7 actually as a number, as you might be able to guess now that we've said it that much. It must be doing something like treating it as the actual minus operation applied to some number 7. So it's actually doing some processing to actually evaluate this. And so if we actually say as.list of E4, we see indeed that underlying it, when R parses this code, when R sees this and is actually trying to then go evaluate that, it actually says, oh, that's a minus. I think of R, I think of that as an operator. So I'm calling minus with a single argument, and that's actually going to produce the value -7 as an actual object. So I will stop there, and we'll talk a little bit more about these language objects in the parse tree on Wednesday, and then we'll launch into the next unit on Python.